Hello everyone, my name is Serhan Gül. I'm a researcher at Fraunhofer HHI at the Video Coding and Analytics department. In this talk, I will present our IBC conference paper, Interactive Volumetric Video from the Cloud, which is a joint work of Fraunhofer HHI and Deutsche Telekom. With recent advances in immersive capture and display technologies, many different use cases emerged that integrate virtual persons into real environments. The goal is to provide a feeling of virtual presence and emulate the actual human interaction in a mixed reality environment. Imagine, for example, that you can take a private lesson from your favorite basketball player to learn how to perform different dribbling techniques, and you can do that anywhere and anytime as you wish, just wearing a pair of smart glasses. However, there are several different challenges that need to be addressed to be able to realize such use cases. First of all, we need a way to capture representations of persons in a photorealistic way. Secondly, we need to create the content such that it can be modified after capture. In other words, we need animatable content, and we need a natural way of interaction with the captured content. And lastly, we need to be able to render those interactive representations in real time and stream them efficiently to mobile devices like mixed reality glasses. Think about, for example, HoloLens. In this talk, I will outline our solutions for these challenges, namely free viewpoint volumetric video for capturing high-quality representations, interactive animation techniques to go beyond the captured content by altering and animating the virtual persons, and a rendering architecture called split rendering that offloads the heavy rendering to a powerful cloud server to reduce the burden on the mobile end devices and achieve real-time rendering. So let's first take a look at the production of volumetric videos. The main idea of volumetric video is to capture a scene, usually with a moving person in it, from all directions using multiple cameras and reconstruct a dynamic 3D model of it. To achieve this, Fraunhofer HHI set up a volumetric studio in 2017, shown on the left side here. And on the right, you see one of the first productions in the studio, where the person is captured by 16 stereo camera pairs simultaneously from all viewpoints, covering the full 360 degrees. The result is 16 synchronized stereo video streams that are then used to create the volumetric video. After the synchronized capture, we first apply various post-processing steps like color grading and keying, and then we use a depth estimator to generate a depth map from each stereo view. Then we store those as color-coded values in a two-dimensional image, as you see on the left, and we fuse the depth information of all 16 stereo pairs, and then we obtain a 3D point cloud, which we convert to a mesh by a surface reconstruction algorithm. After meshing, a mesh reduction step is needed because the depth-based surface reconstruction algorithm creates a high-density complex mesh with millions of vertices and faces, which is not suitable for interactive applications. And the final result of our production workflow is a reduced mesh, and there is also a texturing step, so it's a reduced textured mesh. So far we looked at the capture of volumetric videos. Now let's take a look at how to create animatable interactive volumetric videos. Or in other words, how we can reanimate and alter an actor's performance so that we can achieve an interactive experience. Animation of volumetric video mainly consists of three processing steps. The first step is temporal processing that aims at creating a temporally consistent mesh topology by keyframe-based tracking. The second step is semantic enrichment, where we enrich the captured high-quality data with semantics and animation properties by fitting a shape-adaptive human model. And the last step is a hybrid animation step that exploits the captured content as much as possible to create new animations in a realistic and natural way. So now we'll look at each individual step in more detail. In the first step, temporal processing, we create temporally consistent mesh subsequences, which are basically groups of frames that share the same connectivity information. This has several advantages. First of all, this allows manual editing of textures and corrections of geometry over multiple frames. Also, we achieve a low complexity model, which is good for streaming to mobile devices. And also, we reduce the data sizes due to the temporally shared mesh connectivity. So we only need to encode once for a mesh subsequence. On the left side, you see that the mesh connectivity may differ substantially between consecutive frames. So our mesh registration approach eliminates this and achieves temporal stability, as you see on the right. But keeping the same connectivity for the entire sequence might not be feasible if there are large scene changes. Therefore, we adapt the keyframe concept from video compression and divide the sequence into groups of frames that share the same connectivity. Also, texture images become a video-like stream, shown on the right, that can be compressed very efficiently using a video encoder. With our approach, we are able to register meshes with 50,000 faces in a few seconds computation time on a single machine and with high accuracy. You can find more details in the paper here. In the next step, we want to add semantics and animation properties to the volumetric video. To achieve this, we fit a shape-adaptive body model to each frame and pass the pose and animation information from the model to the captured data. We learned this model using a data-driven optimization process from datasets of multiple captured humans. And as you can see in the video on the right, in order to produce natural movements and animations, the model's shape should resemble the captured data, both the subject and the pose, as closely as possible. So we start from a rough manual alignment for the first frame, and we optimize the pose parameters by minimizing the distances between the corresponding vertices of the model and the captured mesh. In this way, we enrich the captured data with semantic information on pose and animation properties, and we essentially make the volumetric video animatable. In the final step of animation, we perform a kinematic animation of the captured data using the fitted body model. So from the previous step, the individual volumetric frames are already animatable since we enriched the data with animation and pose properties. But in order to attain a high realism, we want to change each frame as little as possible. So we exploit the captured content as much as possible to create the new animations and motion sequences in a realistic and natural way, because the captured content contains natural movements with all the fine details. In this way, we are able to generate new poses of the person that were not captured in the original sequence. An example application is shown on the right, where the head pose of the actor can be modified interactively, for example, depending on the position of a user wearing AR or VR glasses and viewing the actor from different perspectives. So here's a summary of the capture and processing steps for the production of animatable volumetric video. First, we capture stereo pairs and create textured meshes out of them, and then we make those temporally consistent by a mesh registration approach, and then animatable by fitting a body model, and then finally we apply a kinematic animation technique and obtain the animatable volumetric video. So at this point we have the animatable content ready. Next, we'll look at how we can store and stream this content to mobile end devices in an efficient way within a server-client infrastructure, and also how we can achieve interactivity with the user. So after the creation of the animatable volumetric video, we have textured mesh sequences with a period n, meaning that each n consecutive frames are temporally stable among themselves. Then we compress the individual components, mesh, texture, and audio separately, and we obtain elementary streams that are multiplexed into an MP4 container as separate media tracks. For mesh, 3D coordinates and associated 3D normal vectors change at each time instance, while the texture coordinates and faces remain unchanged due to the temporal stability. So at this point we have the content ready as a bit stream in the MP4 file. This could be stored anywhere, ready for playing. And when we want to play, we revert those steps, so we demultiplex and decode accordingly with the appropriate decoders. And then we render a view from the volumetric video using a 3D experience engine like Unity or Unreal. If you are not playing a keyframe, we just update the existing mesh. Otherwise, we create a new key mesh. At this point, one can expect that the volumetric video stored as MP4 can easily be transmitted to a mobile device and played in this form. However, processing of the volumetric content requires high computational power, and it's currently unfeasible to perform the rendering on a mobile device. So rendering even a single object is a very demanding task for today's mobile devices, and multiple objects and animation increases the rendering complexity further. To mitigate this, we developed a system that offloads the rendering to a powerful cloud server and only sends the rendered 2D view to the client instead of the full volumetric content. And then we adapt this rendered view based on the user interaction, for example, depending on the user's head pose and position. At the client side, we decode the compressed video and remove the background. And then we place the object on a 2D plane, which is then integrated into the scene. Since cloud rendering adds additional latency to the framework, we located our server on a 5G edge cloud in order to reduce the network delay. We also have other optimizations in our system for latency reduction. And now we'll look at the architecture of our edge cloud server in more detail and look into some of these optimizations. Our server consists of several different blocks. We won't go into the detail in all of those blocks, but just briefly talk about the most important ones. So we have a volumetric video player that decodes mesh and video data using a GStreamer-based media pipeline and passes the decoded textures and meshes to a Unity renderer. We can also play multiple volumetric objects simultaneously by running multiple instances of the volumetric video player. And we have a Unity framework that's based on user interaction, decodes the obtained meshes and animates them. And then it renders the corresponding view based on, for example, the user's head pose. And then those rendered textures are passed to a GStreamer-based media pipeline. And the media pipeline compresses them using a hardware video encoder from NVIDIA called NVENC, which provides ultra-low latency video encoding. And then those compressed 2D textures are streamed using WebRTC over a network, for example, a mobile network. For WebRTC signaling and interaction metadata, we have a WebSocket server that establishes a session between the client and the edge cloud server. And we also have a controller module that manages the objects, data, and control interfaces. Finally, we have a prediction engine that attempts to predict the future user position for a given prediction window so that we can reduce the effective interaction latency, or in other words, motion to photon latency experienced by the user. So to sum up, a combination of 5G, edge computing, hardware video encoding, and head pose prediction brings low latency to our system, and we are able to provide a smooth user experience. In our preliminary tests, we reached about 60 milliseconds of end-to-end latency with the server located on an Amazon EC2 cloud instance. So you can imagine that locating the server on an edge cloud would decrease that latency even further. Now we'll look into a short demonstration of our system in the next part. So let's go there. Here's a short demo of our system showing two virtual humans integrated into a real environment. So let me play the video first.
Hey, I hope you enjoyed our training session. You don't need a basketball arena to be great. You can practice whenever, wherever. I'll see you at the next Telecom Baskets Bond game, or in the headset. Hey, I hope you enjoyed our training session. You don't need a basketball arena to be great. You can practice whenever, wherever. I'll see you at the next Telecom Baskets Bond game, or in the headset.
So you saw in the demo that the virtual person on the right-hand side, the basketball player, turns his head depending on the user's position and kind of follows the user with his head or his gaze. At each time point, each volumetric object is rendered on two different 2D planes, one for each eye, in order to achieve a stereo view at the client side. And in the background, there are a lot of operations going on at the rendering server. For each object, the server decodes and animates the meshes, performs the video compression, and streams the content using WebRTC. And as you can see, the latency is not really visible to the user due to our optimizations targeted towards low latency. So we recorded this demo using an Android phone for the sake of easy recording, but we also have other clients for Unreal Light mixed reality glasses and web browsers capable of using WebXR. So to summarize, our work integrates several different technologies in order to bring interactive volumetric video to end devices. First of all, we developed a fully automatic capture and processing workflow for volumetric video. And then to obtain animatable volumetric video, we first register the mesh sequences and achieve temporally stable sequences. And then we fit a shape adaptive body model and use a hybrid example-based animation technique to achieve a photorealistic animation. For efficient storage and streaming to mobile devices, we compress each component of the volumetric video separately, and we use efficient mesh and video encoders to compress them. And finally, we developed a server client infrastructure to animate and render the volumetric video in real time and stream to mobile end devices with low latency and bit rates. And with this, I conclude my presentation. Thank you for listening. Feel free to check our IBC paper for more details, and please contact us if you have any questions. And here are some references to our publications if you want to learn more about our work. Thank you.